Where do we get our energy from? And where do we use it? Welcome to watch the sustainability trends in business. This time we will talk about global energy production and use. Energy is the pain point of climate change. Most of our emissions come from energy production, and there are relatively few options available for low carbon production. There are a limited number of primary energy sources available, mostly fossils, bioenergy, hydro, solar and wind. How much of which do we use now? And where do we use it? Where does it go? Why do we need it? Let's jump straight to the deep end with this very busy Sankey diagram. This tells it all. The units are in petajoules, but here the important thing is relative size of production methods and uses instead of how many numbers there are in peta. Well, 15 zeros actually. The total energy use in the world, according to the IEA, was approximately 400 exajoules or 400,000 petajoules in 2020. The numbers are so huge that they do not usually make sense. But you can use the width of each stream in this diagram because they are in linear relationship with the actual size of the stream in the real life. Also, please note that this diagram is not according to the best practice because this mixes heat and chemical energy and electricity, everything together with joules. Well, the error that comes from the exergy versus energy discussion is, it's not insignificant, but it's so small that it doesn't change the big picture. And as a comparison, so if the total global is 400,000 petajoules, then the final energy use in Finland is around 1,300 petajoules, which is about 0.3% of this global use, or 360 terawatt hours if you want to express it in those units. These numbers and this diagram is from 2020, so from a couple of years back. No newer diagrams are available from the IEA, but the big picture is the same, even though the numbers are a couple of percent higher and the fraction of renewables has increased a lot, but it's so small that it doesn't make a difference yet. So on the left we have primary energy. Oil, coal and gas are the big ones. And this is of course not good news at all. Then we have waste and bio, not insignificant, quite a lot actually. But unfortunately of this bio we talk about global south traditional wood burning, which is inefficient and quite polluting. It's not good use for that biomass, so it's not that great. And when we talk about waste, we talk about waste incineration, which is quite often done in very inefficient units with very little emission control. So again, something that is not that great. Of course, the efficient use of biomasses and waste is very, very important in the future, but that's not something you can see from this diagram. And then in the bottom we have the low carb diet. Geothermal heating is here. It's an interesting one. It's probably volcanic, so if you happen to live in an area where you can get heat out of the ground, then you use it, like Iceland. Then finally we have hydro and nuclear. Where are wind and solar? Well, it is this other production. They are growing fast, their share is not that big. Maybe this year they are together larger than hydro, possibly, but small nevertheless in the big picture. Of course, if you remember something about energy and exergy, solar, wind and hydro mean here electricity. So of course their value is higher than their energy content because they are full of exergy. But again, the error is small if you compare the size of these fossils to the size of these low carbs. Then we have the exports in this diagram. It's a little bit of a silly thing because we are talking about global things. So if we had exports, then aliens would most probably have their tentacles in it. So they should match with the imports. The same diagram is used for different countries where it makes sense. And here we have power plants. Power plants are something that convert energy into another form of energy. Most often chemical energy, that is something to be burned, is then converted into electricity. And as the process is very lossy, in case of burning anything, power losses are approximately the same as useful production. Some of the output of the power plants goes as heat, and it's used for premise heating, like district heating in where we live, but then again, that's not a major use in the global setting. On the top you can see oil refineries. They take crude oil in and produce something that we use. It might be gasoline, diesel, jet fuel, and so on. These are the conversions. On the right we have the use of energy products. So why we actually need all that energy. These categories may again need some interpretation. Industrial is quite clear, and transportation, I think. But this other is mostly heating, because space heating is actually, so all the buildings and where we are, where we live, where we work, heating, that is actually the largest energy consumption segment in the world globally, and also the most important segment for carbon emissions. Then we have non-energy, which is chemical use of fossils. Almost anything, of course, if you look at these streams, is used almost anywhere, but there are some quite clear trends. Industry uses everything. Processes use coal, oil, gas. They use them for heat production. They may use them in processes. And also industry uses a lot of electricity. And of course, there are a lot of different branches of industry. Transportation runs on oil. Cars use oil. Ships use oil. Electricity, yes, we use it, but it barely shows in here. Biomasses are used for heating, but also natural gas, oil, and electricity is used for heating. Again, one thing where we use almost anything we have. Non-energy products are mostly petrochemical things, like plastics and polymers from oil. So to cut our carbon emissions, we need to do something about the three top streams. We need to cut them away from this image. But if you cut them away from this image and look at the right-hand side, there will be a shortage of almost anything if we do that immediately. So it is really not a small problem. We can also have a look at this from a different perspective. Here is the primary energy consumption by energy form. The image is pretty much the same, but then you can notice that at some point around 2010, someone realized that burning coal was not a good idea. We should do something about it, and it was replaced by gas. There are large regional differences. Different countries have done different things, but if you want to know more about replacing coal by gas, you can go and ask the Germans. They know everything about it. And when you look at this graph, again, you can note the traditional biomass in there. It's a problem, not a solution. We need to be able to scale the ones on the top very fast. As we are burning a lot of stuff to produce energy, it matters what we burn. Different fuels have different emission factors, which means that when we burn some fuel, the amount of carbon dioxide emitted to the atmosphere per energy unit is different. Usually it's expressed in kilograms of CO2 per megawatt hours, as here. So remember, this is heat, not electricity, which is the output, despite using megawatt hours here. There are a lot of fuels in this list, but if you look at the top of the list, then you can see peat from peat bogs. It's high up, so it's very high emission fuel. Lignite, anthracite and subbituminous coal, there are different coal types for energy use. Different oil products, and there are a couple of them, but they are at approximately the same level of emissions. Even though if you're using highly refined oil products, then you have refinery losses which might be around 10 to 20% of the energy content, which means that they are of course worse to burn. So if you can burn crude oil, that's of course a good thing. Then again, it's not technically that easy. And then finally, at the bottom you can see natural gas. It's at a clearly lower level, but not zero. Wood, by the way, would be on the top of the list at maybe 420 kilograms of carbon dioxide per megawatt hour. It's highly variable, depends on the type of wood you are burning, it depends on its moisture content and so on. But of course, wood is sort of renewable, and then that's a complex issue, but it's good to remember that the immediate effect or impact of burning wood is actually quite high. So here you can also see the problems transforming from coal to gas. Yes, if you change from a coal-fired power plant to a gas-fired power plant, you save maybe 40% of emissions, which is great, but then you've driven yourself into a dead end with no way out, because you can't do that again to get another 40% of emissions out. Then you are left with a fossil fuel. These numbers don't take methane emissions into account. There are significant methane emissions in fossil fuel production. Coal mines emit methane, and of course, if we have oil wells, if we get methane out of ground, there are leakages, and that is also a very important emission source. There are claims that actually natural gas is almost as bad as coal due to these methane emissions. But if you have been watching this lecture series, you know that methane is sort of a short-lived problem instead of being as bad as carbon dioxide. Anyway, the most important lesson here is stop burning fossils. And then again, you can simplify it by saying that stop burning. As huge quantities of oil, coal and gas are burned, there is of course huge economy around them. These markets are several percent, maybe over 10% of global GDP, and it means that there is a lot of coal trade, oil trade and natural gas trade in the global markets. Let's have a look at that. Oil, of course, is easy to transport by using tankers and pipelines. Its global price level is not so much limited by transportation. You can get it where it's needed. But then the producers have a cartel, OPEC, which tries to maximize their returns. That means that if the oil price is falling, then OPEC tells its members to reduce production. So they have production quotas that they are sort of agreeing together. And if that cartel was between companies in the Western world, it would be utterly and completely illegal, but as an international cartel, it works. There are a couple of oil producer countries which are out of OPEC, and that sort of makes the price formation a bit more market-based. The production cost of oil is very different in different places, by the way. And of course, geopolitical issues have a huge impact on oil price. So if you take, for example, the Russian oil, its price for the producer is much lower than its price for the consumer, because there are very high customs duties in between. Also, there are different types of oil, so it's not just crude oil. You can have heavy crude oil, you can have light crude oil, the difference being the length of the carbohydrate chains chemically. But the idea is that light crude oil is easier to refine into, for example, gasoline. And then you have something called sweet and sour. They don't have much to do with taste, but the point is that sour crude oil has a lot of sulfur in it and sweet doesn't, and that sulfur is a problem in refineries. So there are a little bit differences and they have different prices, but again, the price difference due to the quality is not that big. There are severe production bottlenecks in refineries. And this is because large refineries are built to produce different products in certain ratios. So you can make gasoline or diesel out of any crude oil, yes, but your refinery is configured to use specific crude oil and produce specific amounts of gasoline and diesel and jet fuel and whatnot out of it. And making reconfigurations is difficult, so this system is not flexible. And this may lead to a situation where, for example, gasoline is cheap because the demand is lower than what the refineries produce, and diesel is expensive because the demand is higher. During the COVID epidemic, very interesting things happened because the jet fuel, Jet A1, was not produced in large quantities. For example, there was a shortage of certain cables because the plastics used as the insulation material of the cable were such that their raw materials came as byproducts from the jet fuel production. So it is a very complicated value network. Coal is also very easy to transport. It's the easiest. You just pack it into a ship. For example, Finnish power plants have used a lot of Australian coal from the other side of the globe because the transportation cost is so low. There are different types of coal. There are lignite, bituminous anthracite. The difference is technically the age of the coal. If you have old coal, so from hundreds of millions of years ago, you have quite little anything else apart from carbon in it. And if you have young, which means that like 10 million year old coal, then you have a lot of other stuff in there and it's not as good as a fuel. So anthracite is the oldest, purest, energy densest, and then lignite or brown coal is the worst. And the price depends on these factors. Gas is also widely available. Its transportation is easy through pipelines within the same continent, but much more complicated overseas because you have to liquefy it, you have to put it in a very cold form into LNG ships that are designed for transporting LNG, and then you have to have LNG terminals where that liquefied LNG is evaporated. And this means that the price difference between continents where you need to have marine transportation may be very significant. And this actually happened in 2022. At some point, the cost of natural gas was about $30 per megawatt hour in the US and $300 in Europe. At the moment, and this is early October 2024, oil costs about $80 per barrel. And this equals to 45 euros per megawatt hour. Coal costs about $150 per ton, and that's anthracite, the good one. And it's around 20 euros per megawatt hour, so clearly cheaper. And then we have gas, which is about 40 euros per megawatt hour. It is rather typical to have oil and natural gas at the same price point. Coal is usually cheaper, but then you have to add more of carbon trading cost, especially in the EU, which is about 30 euros per megawatt hour for coal. Then it becomes more expensive. For electricity production, gas is currently cheapest because gas-fired power plants have highest efficiency and the emissions are not that high. But these costs are connected together through the use of different power plants. So this is what we do today and what we use today. But what can we do in the future? Well, we, for example, run out of oil. Let's start with the total consumption, which is 170,000 terawatt hours per year. And now, if you have been careful, you notice that in the diagram before, the total consumption was slightly different. Well, that happens, and the numbers seem to be a bit different depending on where you take them from. Are we running out of oil? Well, the proven reserves are about 1.7 trillion barrels or 3 million terawatt hours. That would cover all consumption for less than 20 years, so if all the energy was produced by oil. But currently we are using about 1/3 from oil, which means that there will be maybe 50, 60 years worth oil at the current consumption rate. Proven reserves. For coal, proven reserves are 10 trillion tons or 7 million terawatt hours. This would cover all consumption for 40 years, but again, coal is about 1/3, which means that the coal itself, there will be coal for over 100 years in proven reserves. Proven natural gas reserves are around 200,000 cubic kilometers, which doesn't usually say anything, but it's about 2 million terawatt hours. It's more than 10 years for all consumption, but of course the current consumption is less. It's a bit less than for oil and gas, giving about 50 years in known reserves or proven reserves in rough numbers. And of course, note that these are proven reserves, not the total reserves. They are something that we know where they are and how to exploit them. For example, there is very little coal exploration because we know that there is so much coal that it's not going to be a problem. There is a lot of oil exploration, and it's more likely that we know the oil reserves, even though then there is something called shale oil, which is a very, very bad thing, but huge reserves. In any case, we are not running out of fossils anytime soon. If we burned all the proven reserves, we would introduce about 3,500 gigatons of carbon dioxide into the atmosphere, which is roughly twice compared to what we have put into our largest junkyard this far since the start of industrialization 200 years ago. So that's the problem. Where are the solutions? Will biomasses save us? Sustainable potential is estimated to be 50,000 terawatt hours per year, and getting there requires a lot of careful planning, and that might be an optimistic estimate. There are a lot of biodiversity impacts on wide-scale use of biomasses. Currently, we are using about 7,000 terawatt hours per year, which means that we can maybe make it sevenfold. And that means that we can cover roughly 1/3 or 1/4 of the total energy need by biomasses. So it is a solution, but it is not the solution. Then we have the zero-carb electricity sources. Hydropower, hydroelectric power is now at 4,000 terawatt hours per year, and the estimate is that the exploitable is 16,000 terawatt hours per year, so quadruple. But exploiting this is difficult. It's partly in quite small streams, it's in the global south, it's in uninhabited areas, difficult places. Large dams have huge local ecosystem impacts. And even then, if we used all this, we would have only 10% of the need. So hydropower is not the solution. It's very important from the electrical network point of view, but it's not the solution to our low-carb needs. Wind is now at 2,300 terawatt hours per year, and this is actually from 2023, and most probably it's much more right now. So it's increasing tens of percents per year. The exploitable may be 1 million terawatt hours per year, which is more than enough. Solar is at 1,600 terawatt hours per year, with the same caveat that it's probably more today. And the exploitable potential is 200,000 terawatt hours per year if we use only 1% of the land area for solar production. Of course, we can then have more efficient panels or floating solar and so on. Again, a lot. Nuclear, not renewable but low carb, is at 2,700 terawatt hours per year, and the potential would be 300,000 terawatt hours a year, double our total need at 130 USD per kilogram uranium price. And if we take new technology, the breeder reactor technology, then it's practically unlimited. So we have some essentially unlimited production forms: wind, solar and nuclear. They have their problems though. Wind and solar depend on weather, And nuclear depends on politics, it's capex heavy, there are security issues, and the safety side is not so much the reactors going kaboom, it's more that you can produce nuclear weapon materials by nuclear reactors, and that is a problem if you're trying to give these reactors to, for example, Global South dictators. It is important to note that non-carbs produce primarily electricity. This is why electrification is the direction we need to take to reduce emissions. We need to electrify everything we can, because we can produce electricity without producing excessive emissions. Burning is bad, and it's bad even with biomasses. We need to use the biomasses for chemical production, most likely. So this is the big picture. In the next episode, I will dig deeper into the very important topic of electricity. See you then.